Good afternoon, everyone. Today we'll discuss collimation and ray tracing through lens systems. Have you ever wondered how light from a fiber optic cable can become a perfectly parallel beam? The answer is a process called collimation. It converts diverging light into a beam where all rays travel parallel to the optical axis. To achieve this, we use a converging lens. The key requirement is simple. Place the light source exactly at the front focal point. When this condition is met, every diverging ray exits the lens parallel to the optical axis. The thin lens equation predicts this. When the object distance equals the focal length, the image distance approaches infinity. Physically, that means the rays never converge again. They stay parallel indefinitely. Now, in practice, perfect collimation is actually very hard to achieve. Why? Because real light sources are not ideal point sources. A fiber tip has a core diameter of about 100 to 400 micrometers. Light comes from every point across the core, not just one spot. Each point gets collimated in a slightly different direction. The result is a residual divergence angle. It roughly equals the source diameter divided by twice the focal length. This creates a design trade-off. A longer focal length reduces divergence and gives a more parallel beam. However, a longer focal length also makes the system bigger and the beam wider. Engineers must balance beam quality against system size. Another key factor is the numerical aperture, or NA, of the fiber. It tells us how widely light fans out from the fiber tip. NA is defined as the sine of the half angle of the divergence cone. For example, an NA of 0.22 means a half angle of about 12.7 degrees. If the lens is too small to capture the full cone, the outer rays miss the lens entirely. That means you lose optical power. Now let's talk about the lens type. Engineers often use plano-convex lenses, which have one flat side and one curved side. The orientation of the lens matters. The flat side should face the source, and the curved side should face the output. This arrangement minimizes spherical aberration, where different zones of the lens focus light at slightly different points. The radius of the curved surface is related to the focal length. A shorter focal length means a more sharply curved surface. Now, here's something students often overlook. Positioning tolerance. Even half a millimeter of displacement can make the beam converge or diverge instead of staying parallel. Short focal length lenses are especially sensitive to this. A 19mm lens needs positioning accuracy within a few hundred micrometers. To visualize all of this, we use a technique called ray tracing. We draw individual rays from the source, through the lens, to a screen. The thin lens model tells us the exit angle equals the incident angle minus the ray height at the lens divided by the focal length. By tracing rays from the center and the edges of the source, we can predict the beam size at any distance downstream. To summarize, collimation places the source at the focal point of a converging lens to produce parallel light. Real sources introduce residual divergence, and the choice of focal length involves a trade-off between beam quality and system size. For the next class, please review Chapter 7 on aberration correction and aspheric lenses. See you then.